Namaste everyone. Hope all of you are well. In lecture number 1, lecture number 2 and lecture number 3 in this chapter chemical equilibrium, class 11, chapter number 7, we have discussed that how the rate of reaction increases, decreases. We have discussed about the chemical equilibrium constant at concentration and pressure. In this video we will discuss about Le-Chatellier's principle. First of all, you should know what is this principle, and according to this principle what things happen. So as I have written on the board, you can see that what is Le-Chatellier's principle. If I talk about, according to this principle, if a system at equilibrium is subjected to a change of concentration, pressure or temperature, then the equilibrium is shifted in such a way as to nullify the effect of change. First of all, this principle, for what purpose they have given? They have just given for the chemical equilibrium and the physical equilibrium, what the things happens and which type of change occurs in this type of reaction. Especially it is given for that. So as I have written, according to this principle, the system at equilibrium is subjected to change of concentration, pressure and temperature. Then the equilibrium is shifted in such a way to nullify the change, nullify the effect of change. Means first of all you should know that this system is affected in chemical equilibrium or physical equilibrium. This is specially affected in both the cases. If I talk about, it is affected in chemical equilibrium in such cases like change in concentration, change in pressure and change in temperature. If I talk about the physical equilibrium, then it changes in the specially melting system or melting of ice water system, after that water to water vaporization or water vapor system, and solubility of gases. We will discuss all the things in the detail. First of all, now tell me that Le-Chatellier's principle, the change of concentration, the first point is change of concentration. If I talk about change in concentration, then in an equilibrium, as the concentration increases of the reactant, the result is shifting the equilibrium in the favor of products while increasing the concentration of the product. As a result is shifting in the equilibrium in the favor of reactants. Means as there is a change in concentration, you know very well in any equilibrium reaction, as the concentration change, if we talk about the concentration of the reactant or concentration of the product, in any favor if we talk about, then the change in concentration is especially shifting the equilibrium in the favor of product from reactant to product, and while increasing the concentration. The two main points you have to remember, that increasing the concentration of reactant will result the equilibrium in the favor of product, and increasing the concentration of product will shifting in the equilibrium in the favor of reactant. This is the change in concentration. Now if I talk about change in pressure, then remember when I talk about the change in pressure, when the pressure of the system is increased, then the volume decreases. That is proportional. It means if I talk about the total number of moles present per unit volume increases in the pressure, okay? As the number of moles per unit volume increases, so according to the Le-Chatellier's principle, the equilibrium shift in that direction in which there is a decrease in the number of moles. If there is no change, then the number of moles gases in reaction, then the pressure does not change and does not affect the equilibrium. And third one is change in temperature. So if I talk about the change in temperature, if a temperature of the system at equilibrium is increased, then the reaction will proceed in that direction in which the heat can be used. Thus, the increase in temperature will be favor the forward in reaction in the endothermic reaction, and similarly increase in temperature will favor to the backward reaction for the exothermic reaction. See, whatever I have said you about this concentration change, pressure change or temperature change, it will be favored or it will be shifted to the reactant and product only. Whatever the chemical reaction, if I talk about, just to suppose here the chemical equilibrium, N1A plus N2B is M1C plus M2. If this is a concentration reaction, chemical equilibrium reaction, in this chemical equilibrium these are the reactant and these are the products. So first one was in the chemical chain, that change in concentration. As the reactant concentration will be changed, first what will happen? The concentration of reactant will change. So as the concentration of reactant will change, the shifting of favor in the increasing in the side of product, means here this concentration will change and here this will be shifted to this side as the concentration increases of the product. Similarly, if I talk about the concentration of product change, then it will be shifted to the concentration of reactant to this side. Means when we do any change either in the reactant or product side, it will be increased in the next side. If I talk about the reactant, it will increase in the product side. If I talk about the product, it will increase in the reactant side. Second one was change in pressure. Now just suppose if I increase pressure, means what? As according to the pressure you can judge about the volume. The volume will increase or decrease, right? So the volume will increase or decrease. It depends specially upon the number of moles present per unit volume. So that is pressure here. So according to this principle, the equilibrium is shifted in that direction in which the decrease in number of moles. If the number of moles is decreased in the product side, it will be shifted to the product side, and if the number of moles is decreased in the reactant side, it will be shifted to the reactant side. So it depends specially upon the decreasing side of the number of moles. If there is no change, means if I talk about there is no decrease in the reactant or product side, then there will be no changing or no effect in this equilibrium reaction. Now the third one is change in temperature. As you know very well, if you increase the temperature, what will happen? Can you tell me? As you increase the temperature of the system in this equilibrium reaction, then this heat can be evolved or involved. So as you know, when the heat will be evolved, heat is going out of this equilibrium reaction, then there will be exothermic reaction and heat is involved in this reaction, then that reaction will be endothermic reaction. So here the change in temperature, if I talk about, then the increase in temperature will favor in the forward reaction, means reactant to product, this side. Then there is the exothermic, and this side from product to reactant it is a endothermic. So as we have seen here, these three types of changes in the Le-Chatelier principle. Equilibrium is subjected to change in concentration, change in pressure and change in temperature. Then the equilibrium is shifted in such a way to nullify the effect of change. Means really if I talk about that which type of changes will be there, then you can just say that it will be change in the concentration, it will be change in the pressure and it will be change in the temperature in chemical equilibrium. If I talk about in the physical equilibrium means, as I have said, that there will be ice to water, water to water, vapor, and solubility of gas. In the solubility of gases, all the things will come. So here if I talk about ice-water system, that is melting of ice, then you can say that the melting of ice is accompanied by the absorption of heat and decreases in volume, right? So if I talk about ice to water, okay, ice to water, so what will happen, you know? Ice to water, what will happen? Can you tell me? Melting of ice is accompanied by the absorption of heat. It is an endothermic and there will be decrease in volume. What will happen? There will be decrease in volume. If I talk about here, just suppose this is ice and this is water, okay? It is a chemical equilibrium reaction. So here H2O ice and here H2O water. So if I talk about 1 gram, okay? So here, if I talk about the absorption of heat, so in 1 gram, in this 1 gram, there will be 1.09 ml. Okay, if I talk about the heat then, okay, so here from ice to water, if it is converting, then it will become in this 1 gram, it will be 1.01. Why I am taking these other things? You may have seen that, especially when you are going to buy the refined oil pouch. In that refined oil pouch, it is written that it is 1 liter, but it is not 1 liter. you will see there is 910 ml. 910 ml. So similarly here, if I talk about, then 1 gram, that is 1.09 ml, is in the form of solid. Melting of ice, that's why I have said ice water system. So here from 1.09 ml to 1.01 solid change into the liquid, then what the things happen? As you can see here, since melting of ice is an absorption of heat, it is an endothermic reaction, then there will be decrease in volume. What will happen? There will be a decrease in volume. Similarly, if I talk about the water to water vapor, means vaporization of water, what will happen? Can you tell me? The vaporization of water is an endothermic condensation. Endothermic condensation, water to water vapor. If I talk about this reaction, vaporization. So here this was your first reaction, and now if I talk about the water to water vapor. Okay, water to water vapor. This is your water, and this is your water vapor. Can you tell me what will happen? If I talk about the second water to water vapor system, that is vaporization system. In the vaporization system, the equilibrium will shift towards the right side when the temperature is increased. So the rise in temperature will increase the vapor, as you know very well. Rise in temperature, as the temperature will be raised. So water will be converted into water vapor, right? Water will be converted into water vapor. The equilibrium will shift towards the left side when the pressure is increased. And if there is an increase in pressure, then there will be favor of rate of condensation of vapor into water. Thus, the favorable condition for conversion of water into water vapor are a high temperature and low pressure. Means there will be low pressure and a high temperature, then only that water will be converted into the water vapor. So this reaction, as you can see here, with the physical equilibrium water to water vapor system, the vaporization method, how this ice is being converted into water, and water to water vapor, the second one, water to water vaporization system. And if I talk about the third one, solubility of gases. Can you tell me what will happen in the solubility of gases? Gas plus water, that is an aqueous solution. The third one, the solubility of gases, that is gas plus water. Can you tell me what will happen? Gas plus water? You know it very well. I know that gas plus water, you can say me, that is nothing else. It is an aqueous solution. It will be in the liquid form. Aqueous solution. What will be that? That is an aqueous solution. Okay, so this three, that physical equilibrium, if I talk about it, the gas equilibrium, that solute plus solvent, that is equal to solution. The effect of pressure, the solubility of such gases increases with the increase in pressure, which dissolve in a solvent with the decrease in volume. So this was where your Le-Chatelier's principles, effect in the chemical equilibrium and effect in the physical equilibrium. सबसे पहले मैं आपको बता दूं ये होता क्या है Le-Chatelier's equilibrium. When I talk about anything, you should remember, if you are not able to understand any concept, then please drop it down. As I have said you, that if there is a change in concentration, change in pressure, or change in temperature, what are the effects? No effects, nullify effects in the change of temperature, pressure, and concentration. Here you can see what the things that happen in the change in concentration, what the things that happen in the change in pressure, and what the things that happen in the change in concentration. Similarly, if I talk about the physical equilibrium, you can see here, especially if I talk about ice to water, there will be decrease in volume. If I talk about this water to water vapor system, similarly the three things, change in concentration, change in product, change in pressure, and change in temperature. And in the solubility of gases, as you have seen, there is a change in pressure, means solute plus solvent, that is solution, and effect of pressure, the solubility of such gases increases with the increase in pressure, with the dissolve in solvent, with the decrease in volume. Now I will talk about the reaction quotient. Similarly, as you have talked about this Le-Chatelier's principle, now the next topic is about the reaction quotient. In the division, you know, when we talk about the division, there is a dividend, divisor, and one quotient. So here, now the new topic will be related to the equilibrium quotient. reaction quotient. It is denoted by capital Q. Now, as you know very well, your chemical equilibrium reaction M1A plus M2B equilibrium N1C plus N2D, right? This is our chemical equilibrium reaction. So here, if I talk about what are the quotient in any stage, so similarly, as according to the concentration, what will happen? According to the concentration, we were doing that. What are the concentration? You know, equilibrium constant, the concentration of product upon concentration of reactant, right? But equilibrium will be applied only at the equilibrium state. But if I talk about the reaction quotient, it can be applied into the any state. So here, if I talk about the reaction quotient, that the reaction quotient will be the concentration of product. Concentration of product means C to the power N1, D to the power N2 upon A to the power M1 and B to the power. And here I will write at any stage. This is at any stage. But if I talk about equilibrium constant, okay, if I talk about equilibrium constant, then the same thing will be that the concentration of the product upon the concentration of the reactant. At equilibrium state. At equilibrium. Remember the word. What is the difference between this equilibrium and the reaction quotient? So here, as I have written, it can be applied at any stage. This can be applied. It can be applied. It can be applied at any stage, and it can be applied at equilibrium state. So now, one thing you just tell me here. Can we write that Q is equal to K? Means this is your K and this is your Q. So both the things are equal. But here only one thing is that this can be applied at any stage and this can be applied at equilibrium state. So here, if I talk about Q is equal to K, then what do you see? This is only at the equilibrium state. Remember, this Q is equal to K at the equilibrium state. Yes? Every state it is not equal. Only at the equilibrium state. But if I talk about greater and smaller, when the Q will be greater than K and when the Q will be smaller than K. Remember always, when there is a forward reaction, means a reactant converted into product, that time the concentration will be greater than Q. Means in forward reaction. Forward reaction means A plus B is equal to C plus D. And when Q is greater than K, in backward reaction. Backward reaction means C plus D is equal to A plus B. Right? So here Q is equal to K, the reaction is in equilibrium state. Then the rate of, similarly remember, in forward reaction what happens? The rate of reaction increases, and in backward reaction the rate of reaction decreases. So here you can see in forward reaction the rate of reaction increases. In forward reaction, rate of reaction increases. You can write here. That's why you can see. And in backward reaction, the rate of reaction decreases. Right? So as you have seen here, that Q is greater than K in a backward reaction, so K is less than Q, so that's why the rate of reaction decreases. And here the equilibrium constant is greater than Q, so you can see it is in the forward reaction, so the rate of reaction will increase, and Q is equal to K, that is it only and only at the equilibrium state. Now I will give you one reaction. That reaction you have to show that when it is equal, when it is small, when it is greater. Suppose PCl5, phosphorus pentachloride, PCl5, it converts into PCl3 and Cl2, right? Is this an equilibrium reaction? Yes or no? Definitely it is an equilibrium reaction. If I talk about the degree of dissociation, that also you know very well. Backward reaction rate of observed particular vapor density and the principal theoretical vapor density, that's normal vapor density. If I talk about degree of dissociation in this reaction, what will be the degree of dissociation? dr minus do upon, can you tell me what will be the formula? That degree of dissociation, dr minus do upon do, or you can write that capital D minus small d upon d, right? Now you can ask me, sir, what is this capital D or small d? It is, capital D is the principle of theoretical vapor density, means it will be given you in the question, that is normal vapor density, and small d, that is observed or practical vapor density, or you can say it is an experimental vapor density at the higher temperature, and alpha is degree of dissociation. What is alpha? Alpha is degree of dissociation. So if you want to calculate in this reaction that what is the vapor density is equal to molecular weight upon 2. What is vapor density? Vapor density is equal to molecular weight upon 2. Remember these words. These are the formulas which you should remember. Okay. So now we want to calculate the degree of dissociation and the vapor density. Can you calculate? I'm just making one table so you will be able to understand this reaction. Okay. Now see, first is the reversible reaction. Reversible reaction. Here the initial moles and then the final moles. Moles at equilibrium, or let initial moles and let final moles, or you can say moles at equilibrium. Let initial moles and moles at equilibrium, that's final mole, you can say, moles at equilibrium. Okay, now see, our reaction is PCl5 converts into PCl3 and Cl2. PCl3 and Cl2. Can you tell me what will be the initial moles? PCl3 is one molecule here, you can say that this is 1, this is 0 and 0. In the equilibrium state, what will happen here? This will become alpha and this will become, can you tell me? 1 minus alpha. Since this was 1, this became alpha, so this will become 1 minus alpha. Now in the third box, the total number of moles. Total number of moles. How many total number of moles in the initial moles? It is 1, right? And now here if I talk about, then there is one alpha, and 1 minus alpha I will write here as 1 plus alpha. The total number of moles here, there will be 1 plus alpha. And now NTP means volume at NTP and vapor density. Volume at NTP, normal temperature pressure, and here that is vapor density. Can you tell me what will be the volume at NTP? 22.4 liter. You know very well, that is 22.4 liter. And what's about moles at equilibrium? That volume at NTP. Here that is V0 is just we have to write 1 plus alpha. That 22.4 into 1 plus alpha. Can we write this? Yes or no? Yes. Now I am talking about vapor density. Now vapor density will be, density is equal, vapor density for the reactant, that is 1 by alpha, right? Vapor density will be 1 by alpha, means you can write here volume. But let me write the first volume only, then you will understand. Here it will be volume, reactant of the volume, okay? And what will be the final vapor density? Final vapor density will be, you can say here one thing, that this will be directly proportional, okay? Directly proportional. Density is inversely proportional to volume. Now I am talking about the reactant, and if I talk about the product one, then it is inversely proportional to, means D0 inversely proportional to V0. So now what you have seen here, if I talk about degree of dissociation, what is degree of dissociation? Can you tell me? dr upon d0. So what will be the value here? Degree of dissociation. Correct? Degree of dissociation, the things whatever we have got it, that is vapor density is dr upon d0, that is 1 by vr upon 1 by v0, that is v0 upon vr, right? And now the values are 22.4 into 1 plus alpha upon 22.4. Can we write this thing, yes or no? Definitely we can write. So here, what will be the value of alpha? We want to calculate the value of alpha. So here, 22.4, 22.4 dr upon d0, that is 1 plus alpha. Can we write this thing, yes or no? Definitely we can write dr upon d0 is equal to 1 plus alpha. So what will be the value of alpha, you can say? You can write alpha is equal to dr upon d0 minus 1, or alpha is equal to dr minus d0 upon d0. Can you write this value? See what I have written here. Is it the same? Yes or no? Definitely it is the same. But if I talk about the reversible reaction, then what will be? In reversible reaction and general reversible reaction. General reversible means here, if one reactant and two product is there, then no need to worry. In general reaction, what will be there? In general reaction, N1A, N2B plus N2C. What is there here? In this reaction, you can see the two products are there and one reactant is there, right? So here also no need to worry. The degree of dissociation will be N1 upon delta N. N1 upon delta N. What is this delta N? Delta N is nothing. It is the difference between N2 and N3, right? So here, just the same thing, N1 upon delta N, alpha is equal to N1 upon delta N, dr minus d0 upon d0. where delta n is equal to, can you tell me what is the value of delta n? N2 plus n3. N2 plus n3 minus n1. This is n3, sorry, here. This is n. So here delta n is equal to n2 plus n3 and minus n1. Where delta n is equal to, so degree of dissociation in a general reaction also you can see, or you can write that alpha is equal to mr minus, instead of d density you can write the theoretical molecular weight upon practical molecular weight. If you want to write theoretical molecular weight or practical, so you can write here this thing also, alpha is equal to n1 by delta n into, yeah, theoretical molecular weight and practical molecular weight, mr minus m0 upon m0. So if anybody will ask you what is this mr and m0, you can say them that it is a theoretical molecular weight and observed, or you can say practical or experimental molecular weight. So this is the main thing what we have learned in this equilibrium. So either if I talk about this whole chapter, the things which we have learned is, first of all, you should know about how to write the equilibrium constant in a square bracket, how to write the coefficient. After understanding how to write the coefficient, in what will be the relationship between Kp and Kc, the constant concentration and constant pressure, the reaction constant value. After then delta Ng values we have taken, and then in the reversible, what will be the values of degree of dissociation, and finally the degree of dissociation was the main concept to teach you in this chapter. Hope all of you have understand. If you have any doubt related to this chapter or related to this topic, then please drop your doubt into the comment box section. That's all for today. Thank you very much. If you have not liked and subscribed the channel, then don't forget to like and subscribe the channel. That's all for today. Thank you very much.